The production of precast concrete components at Somoko begins with meticulous mold preparation. Initially, the joints between modular panel surfaces are ground smooth to ensure tight and accurate assembly. Once assembled, the mold is thoroughly inspected for dimensional accuracy and surface condition in accordance with internal quality control protocols. The cleaning phase follows, where workers use damp cloths to remove dust and debris, then apply compressed air to dry the mold surface. A final dry wipe ensures the surface is clean and ready for release agent application, which is not shown in the video but may be inferred from standard practice. Next, embedded items such as lifting anchors, sleeves, and fixings are accurately positioned on the mold based on technical drawings. Precision in this step is crucial for later installation and structural integration. Simultaneously, the reinforcement cage is fabricated manually. Workers cut and bend reinforcing bars, rebars, into specific geometries, including stirrups, hooks, and U-bars. These are assembled into a steel cage by welding or tying at designated intersections. The cage is fitted with plastic spacers to maintain uniform concrete cover and structural integrity during casting. The completed reinforcement assembly is then carefully lifted and positioned into the mold. Workers use alignment jigs or manual measuring tools to verify its placement. The position of each embedded element and reinforcement segment is double-checked against blueprints. Once reinforcement placement is approved, the mold is ready for concreting. A ready-mix concrete batch with controlled consistency is poured into the mold using a chute or pump. Workers use vibrators or tamping tools to ensure thorough compaction and eliminate air voids, promoting uniform strength and surface quality. After pouring, the concrete is left to cure inside the mold for a prescribed duration. Once initial curing is complete and the concrete achieves sufficient strength, the mold is opened. The demolding process is executed manually or with lifting equipment, ensuring no damage occurs to corners or surfaces. The demolded component is then subjected to dimensional verification using measuring tapes, calipers, or templates. Any deviations from tolerances are documented and only compliant units are moved forward. Finally, the finished precast elements are stored, loaded onto transport frames, and dispatched for on-site installation. This production line ensures precision, repeatability, and high-quality structural elements for use in industrial and civil construction projects. The production of StelTech custom welded beams begins at the fabrication facility, where large steel plates are unloaded and prepared. Plates are cut into specific dimensions for flanges and webs using CNC-controlled plasma cutting machines, ensuring precise geometry for each beam segment. The cut plates are marked and organized for assembly. In the beam fabrication line, the flange and web plates are fed into an automated beam welding machine. This equipment positions the plates into the I-section configuration and uses submerged arc welding (SAW) to join the components. The welding process is continuous, creating strong, consistent welds ideal for supporting large structural loads. The beams are then moved along rollers through the welding station as the weld head travels the full length of the joint. After welding, each beam is straightened mechanically to eliminate thermal distortion. Workers inspect the welds visually and with measuring tools to ensure dimensional accuracy and compliance with quality standards. Next, additional elements such as end plates, splice plates, or stiffeners are welded on where required. The beams are then transferred to the blasting area, where shot blasting removes surface impurities and prepares them for coating. In the painting booth, a corrosion-resistant primer is applied, providing long-term protection in the marine environment of the port of Tauranga. The painted beams are left to cure before being carefully loaded onto transport vehicles. At Sulphur Point, the Steltec beams are offloaded by crane and lifted into place for final assembly of the 300-meter-long, 70-meter span structure. The ammunition manufacturing process begins with the strict selection of premium components: brass cases, primers, powders, and bullets. Each material undergoes quality screening for consistency, hardness, and dimensional accuracy before entering the production line. On the automated production line, cases are first cleaned and polished using vibrating tumblers with cleaning media to ensure surface smoothness and remove oxidation. The clean cases are then transferred to the priming station, where primers are mechanically inserted into the case heads. This operation uses pressure-controlled insertion units to maintain precise primer depth and orientation. Next, the cases move to the powder charging station, where electronic dispensers fill each case with a measured amount of propellant. Load cells continuously monitor the charge weights to ensure uniformity. Any deviation from the set parameters results in automatic rejection of the faulty cartridge. At the bullet seating stage, bullets are aligned and inserted into the charged cases. Servo-driven plungers push the bullet to a precise seating depth, achieving tight tolerance in overall length. Following this, the crimping unit tightly secures the bullet in place by applying radial pressure to the case mouth, ensuring reliability during feeding and firing. Each completed round is then sent through a visual inspection system, where high-resolution cameras and sensors check for OAL accuracy, primer seating depth, bullet alignment, and crimp quality. Defective rounds are automatically removed. Before packaging, random samples from every batch undergo functional and ballistic testing. These include pressure tests, velocity measurements, and grouping tests in controlled shooting environments. This ensures each lot meets reliability and safety standards. Finally, the cartridges are packaged using vibration-dampened equipment, labeled, and stored under controlled conditions, ready for fast customer delivery. The hydraulic pipe bending machine bends a metal pipe with a diameter of 115 millimeters and 3.5 millimeters thickness to a radius of 1,200 millimeters. First, the pipe is clamped between the bending die and the pressure die. As the hydraulic system activates, the bending arm rotates around the central die, applying force to gradually bend the pipe. The supporting rollers ensure precise curvature while preventing deformation or collapse. The machine bends the pipe smoothly and evenly without damaging the surface. This method is suitable for steel, aluminum, and iron pipes used in plumbing and construction, especially for adapting pipes to specific angles and layouts. The production of disposable razor blades begins with stainless steel plates. These plates are fed into the system and undergo a hardening and sharpening process to create a precise cutting edge. Once sharpened, the blades pass through a duplication stage where multiple blades are stamped or formed from the same base plate. Next, the blades are injected or assembled into plastic housings to form the razor heads. The assembled heads are then conveyed to the packaging line, where they are grouped typically 10 or 12 pieces per carton. Each carton weighs approximately 36 kilograms. During the final stage, automated systems verify product quality to ensure consistency and safety. The entire process is supported by robotic equipment and controlled by engineers, maintaining high production efficiency and reliability. The finished razors, made from stainless steel in China, are then prepared for distribution. At the trade fair, Simplecamp showcases its high-precision machining of extremely large and heavy workpieces through its double-sheath machining centers. This contract manufacturing process is designed for XXXL components requiring exceptional accuracy and strength. The state-of-the-art facility demonstrates advanced capabilities in job order production, highlighting the machining of oversized steel and cast parts. Visitors observe massive workpieces being milled, turned, and drilled with precise control, ensuring tight tolerances even for components weighing several tons. The process emphasizes flexibility and custom production, meeting the complex demands of sectors like energy, heavy industry, and press manufacturing. Simplecamp's exhibition impressively underlines its expertise in toll production for large-scale, technically demanding projects. The aluminum extrusion process at ILSCO Extrusions Inc. transforms lightweight aluminum into precise, custom-shaped profiles used across countless industries. The process begins with aluminum alloy logs, known as billets, which are cut to uniform lengths and heated in a billet furnace to nearly 900 degrees Fahrenheit until they reach a soft but solid state. Simultaneously, the steel die, container, and support tooling are preheated to maintain a consistent operating temperature during extrusion. This strict temperature control is vital to achieving the desired mechanical properties and profile quality. After heating, the billet is transferred to the extrusion press. Excess material from the previous cycle is sheared off, and a powerful hydraulic ram pushes the billet through the container and the shaped opening in the die. This process, performed with thousands of tons of pressure, forces the aluminum to take on the die's profile shape. As the extrusion exits the press, it is immediately quenched in a water bath to cool it at a controlled rate. A puller then grips the extrusion and guides it along the runout table, which works in sync with the press. The extrusion is cut at the billet seam and moved to a cooling table. Next, it undergoes a stretching process to correct any twisting or warping, and to relieve internal stresses. After straightening, the extrusion is cut into customer-specified lengths at the sawing station. To enhance strength and durability, the parts are placed in aging ovens where they undergo artificial aging to develop final mechanical properties according to alloy and temper requirements. Additional finishing services include deburring and surface smoothing using vibratory finishing machines, which prepare the parts for painting, powder coating, or e-coating. Finally, finished products are carefully inspected, packed, and delivered to the customer. Throughout the process, ILSCO ensures tight process control and quick turnaround, meeting exacting specifications for quality and consistency in every custom aluminum extrusion order. Man-or. The service process for wind energy begins with transporting the drivetrain or gearbox ZF or multi-brand to the European Service Center in Witten. After inbound inspection, the gearbox is disassembled for detailed assessment. Components such as gears, housings, and planet carriers are reworked and precisely measured. Repairs and upgrades are implemented as needed. Following reassembly, the gearbox undergoes a test run, is painted, inspected outbound, and delivered to the customer supporting turbines from 0.8 to 9.5 megawatts. Beta. The Bugo DCIV drive unit moves the FlameTech oxy-fuel torch along a fixed path to cut through the steel coil. The torch generates a high-temperature flame using fuel gas and oxygen, melting through the steel as it travels. The system maintains a steady cutting speed and consistent torch angle, ensuring smooth and precise cuts. This automated setup allows efficient coil cutting with minimal manual intervention, enhancing accuracy and productivity. The Hellerfort 4000 performs 5-axis simultaneous machining of a titanium TiAl 6V4 aerospace component. Rough machining is carried out using a U60mm tool at a cutting speed, VC, of 60 meters per minute, feed per tooth, FZ, of 0.8 mm/Z, and a feed rate of 2 mm. This removes bulk material efficiently. Finish machining is then done with a U80mm tool at VC equals 100 meters per minute, FZ equals 0.13 mm/Z, and a feed of 0.13 mm to achieve precision. The machine mills thin walls with thicknesses ranging from 0.5 to 2 millimeters and conical angles of 1 degree to 3 degrees, demonstrating high accuracy performance in structural titanium parts. The carbon wheel manufacturing process begins with pre-impregnated carbon fiber laminates delivered in large rolls. These sheets consist of unidirectional or woven carbon fibers combined with a resin system. The rolls are unwrapped, cut into segments, and transferred to a vacuum-assisted cutting table. There, an Eastman machine, guided by a computer program, cuts precise shapes used for the wheel structure. These cut pieces are moved to layup tables, where 2 technicians work simultaneously, one handling the male side of the rim and the other the female side. An aluminum core covered in latex serves as the base for layering the carbon plies. The latex helps achieve uniform compaction and prevents fiber shifting during pressing. Once the layup is complete, the preforms are stored in a freezer. This step causes the latex to shrink, allowing the preform to be easily separated from the core. A bladder is inserted through the entire rim and the 2 halves are joined. Final laminate pieces are added to make a complete preform. A protective plastic film remains on the surface until just before molding to avoid contamination. The preform is weighed and documented as part of the quality control process. a tire bed insert is attached, and the preform is now ready for molding. In the molding room, the press is thoroughly cleaned using a brush, vacuum, and chemical wipes. Mold temperature is measured to ensure consistency. The protective plastic is removed, and the preform is placed inside the mold. The bladder inside the rim is inflated, forcing the carbon plies to conform tightly to the mold. Heat causes the resin to flow and cure, producing a void-free uniform structure. Excess resin is wiped off, and the molded rim is weighed and marked again. The rim then moves to the drilling station. Holes are drilled in 2 stages, from the inside for the spoke and from the outside for the nipple. Spot facing is performed to ensure proper nipple seating. After drilling, the rim is wet sanded to prepare for finishing. In the decal room, water transfer graphics are applied, baked onto the rim, and sealed with a clear coat excluding the brake track, which is masked. The rim undergoes final quality inspection and is either boxed or passed to wheel assembly. Technicians install spokes into the hub, lace them to the rim, apply Loctite, and balance spoke tension. Tension is checked by plucking spokes and listening to their tone. The finished wheel is then inspected at 46 checkpoints. If it passes, it is packaged and ready for shipment. Crews begin by floating a prefabricated steel platform onto the river and pouring a concrete deck with 4 large holes. Through these, steel casings were inserted and driven 140 feet below water to bedrock. Each pier had 4 caissons. Workers excavated muck, gravel, and rock from inside the casings, while water remained inside. They then drilled an additional 25 feet into bedrock and installed rebar cages, followed by concrete. A cofferdam was lowered around the work area, and a thick concrete seal was poured underwater. After pumping out the water, workers built footings, columns, and removed the cofferdam. The high-speed blanking process performed by the SA-315 press begins with the loading of the double decoiler, which holds 2 coils of electrical steel. These coils are fed into the system, and the fully automated insertion of the strip ensures accurate positioning for further processing. As the strip unwinds, a coil loop is formed between the decoiler and the press line to allow continuous feeding without tension issues. Before entering the press, the strip passes through a traversing and contactless strip thickness measurement device. This ensures the material meets required thickness tolerances and maintains consistent product quality. The system is governed by the Schuler interlocking control, which synchronizes the functions of all connected equipment, including feeding, measuring, and pressing. With everything in place, the startup of the die is initiated. The press enters a continuous run, blanking out precise shapes of rotor and stator stacks from the strip at high speed. The motorized movable bolster plate allows the tool to be accurately positioned, while the segmented bolster plate offers enhanced flexibility for different tool sizes and configurations. During production, retractable die-changing consoles remain hidden, but can be extended quickly for efficient tool changes. The stack removal system automatically ejects finished rotor stacks from the press, reducing manual handling and improving cycle time. All machine components, from coil feeding to die operation and stack removal, are fully integrated into the press control system, ensuring optimal coordination, safety, and performance. This advanced level of automation makes the SA315 ideal for producing high-quality rotor and stator laminations in large volumes with excellent precision and efficiency. The production of roller chains begins with material processing, followed by punching plates into precise shapes. These plates undergo heat treatment using a German-made multi-purpose furnace and a controlled atmosphere mesh belt furnace to enhance hardness and durability. Shot peening is applied to improve fatigue resistance. The hardness of chain parts is tested, along with metallographic analysis. Chain assembly is performed, and the finished chains are subjected to braking load testing, length testing, and fatigue testing. The chains are then oiled to ensure smooth operation. Additionally, sprockets are manufactured in-house. Finally, the finished roller chains are stored in the warehouse and prepared for delivery. The Junker vibration test compares various locking methods under transverse vibration. An M16 unsecured bolt is marked and tested, showing rapid tension loss. Then, a plain washer, helical spring washer, check lock nut, nylon inserted nut, and double nut are tested, each relying on friction and failing to maintain clamp load. Finally, Nordlock wedge locking washers are tested. Their cam design prevents loosening by creating a wedge effect. The clamp load remains stable, no rotation occurs, and impression marks confirm proper locking. Molten slag is transported using specialized slag pots mounted on rail cars. Upon arrival at the slag dumping site, the pots are carefully tilted to pour the hot slag onto the ground. The slag then spreads out, cools down gradually, and solidifies into large, brittle masses. This process allows for safe handling and eventual recycling or disposal of the solidified slag. Used EV battery packs are first unloaded, tested, and discharged. Functional cells are saved, while the rest are shredded into a damp mass. This mixture is dried and drained of electrolyte, then sifted to extract black powder containing lithium, cobalt, manganese, and graphite. Magnetic and non-magnetic materials are separated, yielding plastic bits, aluminum-copper mix, and valuable metal powder. Volkswagen's process enables up to 95% battery material reuse. The plate bending process is carried out using a robust 4-roll hydraulic system. The process begins with the operator loading a flat metal plate onto the machine's feeding platform using lifting equipment. The material is properly aligned and positioned between the upper and lower rolls. The machine features a 4-roll configuration, a central top roll, 2 lower rolls, and a side roll. The hydraulic system activates the bottom rolls to raise the plate upward, clamping it securely against the top roll. Simultaneously, the side roll moves into position to perform pre-bending. This step reduces the flat ends typically found at the start and end of a rolled plate, ensuring a consistent curve from edge to edge. Once the plate is clamped and pre-bent, the rolling process begins. The operator controls the machine using a user-friendly panel that may support both manual and CNC computer numerical control programming. This allows for precise control over the position and pressure of each roll. As the plate passes through the rolls, the machine bends it progressively, forming it into a curved or cylindrical shape depending on the programmed parameters. Throughout the operation, the hydraulic drive system ensures all rolls move synchronously and with the necessary force to handle thick or high-strength plates. The AHS 30-45 model is capable of bending large and heavy materials with high accuracy. The side supports and optional overhead supports visible in the video help stabilize the workpiece during bending, especially when forming large diameters or conical sections. Head. As the plate advances through the machine, the rolls continuously apply pressure and shape the material. The process is smooth and efficient due to the automatic adjustments enabled by the machine's control system. Once the desired curvature is achieved, the machine stops and the rolls retract to release the formed part. In the final steps shown in the video, the finished cylindrical shell is removed from the machine. The operator inspects the result to ensure it meets dimensional and surface quality requirements. Thanks to the four-roll design and precise hydraulic control, the finished piece shows minimal flat ends, uniform curvature, and no signs of misalignment or deformation. Safety measures are always in place during operation. The machine is equipped with emergency stop buttons and mechanical barriers to protect the operator. These features, combined with the machine's advanced automation and structural rigidity, make the AKBEND AHS 30-45 highly suitable for applications such as pressure vessels, tanks, and structural components. In conclusion, the AKBEND AHS 30-45 delivers high-performance plate bending through a fully hydraulic four-roll process. Its ability to handle thick plates, combined with its automation and safety features, makes it a vital tool in modern heavy metal fabrication.